Hello, everybody. My name is Stephen Tu, and today I'm going to present our paper titled Learning Stability Certificates from Data. This is joint work with Nick Boffi, Nick Matni, Jean-Jacques Slotine, and Vikas Sindhwani. The motivation for our work is as follows. In the past few years, we've witnessed a lot of incredible demonstrations showing very impressive robotic capabilities, from agile locomotion to self-driving cars to impressive robotic manipulation tasks. Given these successes, a very natural question to ask is, what does it take to get these impressive demonstrations out into the real world and interacting with humans on a daily basis at scale? I would argue that in our research community, a lot of the work has focused on two things: algorithmic improvements to train better controllers, and building better models and simulators to more accurately capture complicated tasks. However, there has been less emphasis or focus placed on how to take a given controller/policy and provably verify its correctness in terms of both stability and safety. It is our belief that understanding the limitations of the control policies we design is key to unlocking real-world deployment. In this work, to address this issue, we present an algorithmic framework for provably certifying guarantees for a dynamical system from collected trajectory data. Let me provide an overview of this algorithmic framework. First, we start with what is a very common existing pipeline, where we take a system and control objective and we pass it to a fancy state-of-the-art reinforcement learning algorithm, which then outputs a control policy for the system. We then close a loop by putting this system in feedback with the learned policy, and this gives us our desired behaviors. We'll call the system g of x to emphasize that once we close the loop, it acts as an autonomous system. Now we can introduce the verification framework. We will collect n closed-loop trajectories g1 to gn. We then construct an optimization problem to find a certificate function v such that the inequality h of gi, comma v is non-positive for all the collected trajectories. As we will discuss on the next slide, the certificate function proves the desired stability/safety properties that we want to verify. The output of the optimization algorithm is both a certificate function v and a probabilistic guarantee that on new unseen trajectories, the probability that the safety condition is violated is upper bounded by the dimension of the function class over the number of trajectories n. Notice that this quantity tends to 0 as n tends to infinity. So the more closed-loop samples collected, the more certain we can be about the generalization of our policy on unseen trajectories. As mentioned previously, a certificate function is a function which is used to prove a desired property of a dynamical system. The most well-known example of a certificate function is a Lyapunov function, which is used to prove Lyapunov stability, where all trajectories tend to a desired equilibrium point. A more general certificate function is that called a barrier function, which proves set invariance, which is the condition that all trajectories which start within a given set remain in the same set forever. Another example is a contraction metric, which proves incremental stability, which states that two pairs of trajectories will eventually converge towards each other. Now, one of the key insights of this paper is that each of these certificate functions can be expressed in the form of an inequality condition h less than 0, which we can encode in the optimization on the previous slide. I want to conclude this talk by a numerical example of our framework in action. We learn a Lyapunov function for the damped pendulum, where the downward position is a stable equilibrium point. The learned Lyapunov function is parameterized by a small, fully connected neural network. In the figure, we plot the level sets of the learned Lyapunov function. Furthermore, for the 10-level set, we start many trajectories of the system along the level set and roll the system forward to demonstrate set invariance of the learned Lyapunov function. This shows that the learned Lyapunov function faithfully captures the geometric properties of the pendulum dynamics. In the paper, we also show a few more experiments involving adaptive control on this learned Lyapunov function, an example involving a Minotaur robot, and also an example where we learn a contraction metric for gradient flow in a particular system. Thanks.